Alright, in this video I'm going to discuss metallic bonding. So the first thing I want to remember here is that metals are defined by their low effective nuclear charge. That's why it's really easy for them to lose electrons. So in a most basic sense, when I say metal, I mean an atom that loses its electrons very easily. So let's imagine sodium here, Na. Its atomic number is 11, and we assume if it's neutral then it's going to have 11 electrons. And just using our old model of the atom, that means I have plus 11 inside, 2 electrons in the first shell, 8 in the second shell, for a total of 10, and then I have another shell with another electron. Now recall that when this electron looks into this atom, it doesn't see this as a complex system of electrons and protons, but instead just sees it as one overall object. That overall object would have a charge of plus 11, minus 10, or a charge of plus 1. So that's what we call our effective nuclear charge. Remembering that our effective nuclear charge goes from plus 1 to plus 8, we can see that plus 1 is the low end of the scale. That means as far as this electron is concerned, it's not very attracted to this atom, and so it's free to leave easily. Now, we understand that if a nonmetal, like chlorine, comes along, it can take that electron, and it has a high effective nuclear charge, plus 7 in this case, and so that's a natural thing that will happen, and we call that an ionic bond when that electron is transferred. But lots of elements, let's say copper for example, are very stable just on their own as an element. So how, if this atom is so easy to lose its electron or so willing to lose its electron, can it form a stable material like copper or iron or something like that? Basically what happens, if we imagine the coppers who would have 2 valence electrons, and another copper who has 2 valence electrons, and another copper who I'll give 2 valence electrons to. Basically what happens is these electrons leave their individual atoms. They don't leave the material as a whole, but they no longer exist associated with their individual atoms. What this leaves us then is a whole bunch of plus 2 charged ions, and then a whole bunch of electrons that are floating about in it. And then, while the attraction for any one electron to any one of these charged ions is low, because this electron isn't associated with any one of these positive ions, it can attract to many ions. So instead of this electron being associated with one copper and there being some level of attraction here, this electron can be associated with all of these positive 2 copper ion cores. And so, although the individual attractions are low, it can attract to many ions, and so the attractions add up. So the overall attraction for the electron, not to an individual atom, but to the material as a whole, becomes large. So this is really different from anything else we've talked about, this metallic bond, where sometimes this is called positive ions in a sea of electrons. It's really different from any sort of other form of bonding that we've really talked about. And I can see how there's a little bit of confusion. Is this an intermolecular force or is this an intramolecular force? I mean, it is individual electrons. It is individual electrons attracting to atoms. And then on the other hand, because it's not just one atom, but it's sort of shared between all of the different positive ions, is it intermolecular? This force is typically classified as an intermolecular force because of that electron's attracted to a large number of other molecules. But I can see why that's a little confusing. But what it does is it leads to some really interesting properties. Specifically, since the electrons are not associated with any one atom, but instead the whole material, they are free to move. This allows this material to be electrically conductive. Alternatively, because while the individual attractions are small, the overall attraction becomes large. We get high melting points and boiling points. Finally, again, because these attractions are large, but they're not to a specific atom, we end up with the situation where these materials are hard, but at the same time can be shaped without breaking. So the attraction is large, and that makes the material overall hard. But at the same time, because they're not attracted to a specific atom, because we're not attracted to any specific atom, we can change the shape of the material without it breaking. And this is what leads to these materials being like ductile and malleable. I don't know if I'm going to spell that right. Malleable? Maybe that's it. Anyway, so the idea here is instead of forming a bond, the copper atoms all just let their electrons go. The electrons continue hanging around the positive charged atoms because although they're not really attracted to any one of those atoms, they have a small amount of attraction to a large number of ions in the same region. The overall material becomes neutral. What we end up with is a lot of small individual attractions that add up to a large overall attraction. The large overall attraction gives us high melting points and boiling points and hardness. The freedom with which the electrons can move, or the idea that they're not attached to any one atom, leads to our electrical conductivity, malleability, and ductility. So that's the metallic bond and some of the ways that it leads to the properties of metals.